Yes, thank you, Simone, for this introduction and for inviting me to this workshop. Also, thanks to the organizers for letting me speak first, even though I'm doing it online. I would really have liked to be there, but many of you know that together with my family, we recently moved to Frankfurt and our childcare is still quite incomplete and this poses some difficulties. So in the end, I couldn't manage to come to Bonn, even though it's quite close. But I'm glad to participate at least online, and hopefully I can attend, say, all the talks in the morning and some of them in the afternoon. And well, some of you were present at my talk in Bonn a few weeks ago, which was also online and which was interrupted by my son, this is not going to happen today, I hope, because nobody's here. So I should be quiet this time. Okay, so I will speak about duality in coordinated particle systems. This is joint work with one of the organizers of the workshop and the next speaker. Okay, now it's not moving. Okay, now this is what I want to talk about. So on this slide, there is not yet coordination and not yet duality, but there are particle systems. In particular, we are considering systems of branching and coalescing particles that undergo motion and death. So the transitions we have in our particle systems are branching, coalescence, death, and migration on some lattice, or actually we will rather restrict ourselves to smaller objects. So we work on some lattice or maybe small graph V, where particles migrate at a rate MUV from side U to side V. They may undergo binary branching at some rate R. They may coalesce at a certain rate, and they may die at a certain rate. And in this simple setup that I presented here, you can write that down as a Markov process in continuous time on taking values on N0 to the V, where the generator is given by this formula, where the precise form is not so important, but it's something you've probably all seen before. So this is, by the way, the setup that Andrea and Swart looked at in their paper of, I think, 2005 on branching coalescing particle systems. But I should already say now that what they do is quite different from what we do. So they do more technically demanding things. They look at infinite lattices, where ours will be small. They look at infinite numbers of particles, where we usually restrict ourselves to finite numbers, and they look at long-term behavior, where we look at more simple features. But what we do, we add a special feature to this type of particle systems. We include coordination. What do we mean by that? I want to explain the concept of coordination in a very simple example. Just look at, instead of a lattice, just look at one side, so no migration, and we consider just branching particle systems, but two different types of them. So we fix a branching rate R, and our Markov process, our Markov chain, starting with one particle, denotes the number of particles at time t, where branching may happen either independently, so every particle branches independent of the others at rate R and splits into two, so binary branching, or the other option, all particles present at a certain time branch at the same time simultaneously in a coordinated manner at a constant rate R. So here's a picture below of the two types of processes. The first case is independent branching, which is well known as the Joule process. First picture shows that here. And the second case is what we call fully coordinated branching, because all the particles present branch at the same time. What one sees if one does a few lines of calculations is that actually both these processes at the given time t have the same expectation. So expectation of this process at time t is given by e to the power rt in both these cases. And that's something we can try to keep in the back of our mind, because we will see this phenomenon later on in this talk. So this is what we mean by coordination, is that particles don't move or branch or die or coalesce independently, but in a coordinated manner. So we can generalize this first example a little bit. by not looking just at the two cases, but at the whole class of cases. For this, we fix a finite measure R, which will be our, so to say, branching rate measure, which is a finite measure on the interval from 0 to 1. And we consider the branching process now to be the Markov chain in continuous time, where we start again with one particle that jumps at a rate RZZK from Z particle to Z plus K particles. So K new particles are created, and the rate is given by this expression here, which includes my measure R. And this rate here can be interpreted in the following way. You can think that the U in this place can actually go away. Forget about this U here. So the measure 10 R dy sort of gives you a number y between 0 and 1, which can be interpreted as the probability with which each of the particles present at that time actually participates in the branching event. So we determine a probability according to our R measure, and then each of the Z particles chooses independently to either participate in the branching event and produce an additional, so split into two, or not to participate, and that's why what gives us this expression here with the binomial coefficient. So this is the general way we want to coordinate our transitions. In this case, we coordinate the branching transitions. So in this case, with this finite R measure, we can have certain special cases. One special case is if the measure capital R is just equal to number little r times the Dirac measure at 0, then you see from the expression of the rates that you actually only get one particle branching at the same time. So the only rate that is non-zero is actually the rate at where you produce one new particle, and this is given by RZ. All the other ones are 0 if you plug that in. So we are back in the case of independent branching. So we obtain the Joule process of the previous slide. Another situation is when your measure is a multiple of the Dirac measure at 1. Then if you plug this in here into the formula for the branching, you see that all the rates are 0 except the rate where you jump from presently Z particle to 2 Z new particles, so where all the Z particles produce a new one. So this is the other special case of the previous slide. This is the fully coordinated branching. If you take an intermediate measure between the delta 0 and the delta 1, so if you take R to be little r times Dirac at some number a between 0 and 1, then branching events happen at rate R, fixed rate, and each particle participates with probability A independent of the other particles. So this is another special case. And the most general situation that we want to consider is with this measure capital R. Okay, so this was just for the branching transition, but of course we can do that for all the 4 types of transitions I had on my first slide. So the processes we consider in this talk is the following situation. We consider our V to be a finite set. We could in some cases drop the finiteness assumption, but to avoid technical difficulties, I will always consider it finite in this talk. And we fix for each site or for each point in the set V, we fix measures lambda, D, R, and M, which we all want to be finite measures on 0, 1. And then we call a structured branching coalescing process with coordination the Markov chain ZT, which takes values in N0 to the V, where the transitions are given in exactly this form. So we have here a coalescence of K out of the Z particles into 1 at side U of V. And this happens at a rate which has the form we had before, but now with this coalescence measure lambda. We have death of particles. So K particles die at a certain rate, which is given again in this form with my measure D at side U. we have the coordinated branching, where k new particles are created, and we have coordinated migration from U to V, where k particles move from U to V, again at the rate which has this particular form. Now you probably noticed that here, what we had 1 over y for migration, branching, death, we have 1 over y squared in the case of the coalescence rates, which is of course due to the fact that in order to coalesce, you need 2 particles to participate, while for the other events, just 1 particle does something at the same time. So the possible transitions our Markov chain has are coordinated coalescence, death, branching, or we can call it reproduction, that's why we use R, and migration. So this is the type of processes we want to consider. And just to make sure everybody understands what's going on, are there questions at this point? Okay, doesn't seem to be the case. I don't see you as well as I would in presence, but I'm sure somebody would tell me if there are questions, right? Okay, so we have coordinated particle systems. If we take all the measures equal to Dirac at 0, then we are in the situations where the particles all move independently, so they have no coordinations. This is the situations Atreya and Swart considered in their paper, although, as I already mentioned, they work on infinite lattices and do more complicated things. Now, one thing one should observe is that here we always had these measures here that sort of determined the probability to participate in a certain event. Those measures with the 1 over y in front are not necessarily finite. They have a singularity at y equals 0, but the singularity doesn't bother us if you integrate over the point of the singularity. If you integrate this binomial expression with respect to this measure, then you see that what you end up with is actually finite. And so I already said that, of course, for branching, death, and migration, we have a singularity at 0 of order 1 over y. And for coalescence, we have 1 over y squared. Of course, the same holds true for the coalescence rates. So observing this, you see with a bit of technical details that actually our process does not explode in finite time. So we have a bona fide Markov chain which does not explode. That you can see by looking up the right theorem in Noemi and Kurt and observing that actually the total rate, also because of course we are on a finite lattice, for anything to happen at a certain time is finite by just plugging it in. So in these situations, we don't have difficulties with these technical details. Okay, so we have a nice Markov chain. So coordination is something that you can find in many classical and more recent models that were studied. One very classical case are, of course, the lambda coalescents, where the coalescent is coordinated in exactly the manner we do here. They were introduced by Pittman and Müller and Zagitov in 1999. Another more recent model is where death is actually coordinated. So we have branching in the usual independent manner with the delta 0, and death in a coordinated manner. This is a model by Hermann and Pfaffelhuber, which are called branching processes with binomial disasters. A situation with coordinated migration was actually presented in the talk I gave a few weeks ago in Bonn. That's the Seedbank coalescent with simultaneous switches. I will feature it a little later in this talk in one example. There is the Kingman coalescent with erosion by Foutel-Rodier, Lambert, and Scherzer, related to the hierarchical Moore model of Dawson. There's actually also a situation where you have coordinated migration. There are coordinated branching coalescing processes where both branching and coalescence are coordinated. There are population models in one-sided random environment by Godero and Vichambre, nested coalescence by Blancas, Duchamp, Lambert, and Siri-Gévous. And the last item on my list is maybe, for those who know the parabolic Anderson model, surprising, because actually the parabolic Anderson model is a classical model from, say, statistical physics, if you like, is actually not coordinated at all. But I will also mention it later in my talk as an example where coordination may be useful to prove something for uncoordinated model. So you will see a little in a little more detail what I mean here. Of course, I should also mention that the list is absolutely not complete. There are more examples, and there are also more classical examples that I didn't put on the list. For example, there are, for example, Liggett and Spitzer in 1981, I think, considered coupled random walks, which are actually coupled in the same way as we couple our coordinated process. There's Griffith, within the context of the contact process, who also use this kind of coordination. So it's really not, it's really a natural manner to study these processes, but I think so it deserves a bit of a sort of unified framework, which we were trying to give in our work, to look at this coordination as a conceptual, from a conceptual point of view. Okay, so one first thing one, of course, can look at, or naturally looks at when one considers particle systems, especially if one comes from population genetics, is duality. So duality in this context is the following. So if we have two Markov processes with state spaces E and F, and H, a bounded and measurable function from E times F into the real numbers, then we say that the two Markov processes are dual with respect to this function H if this equation here is satisfied for all values X in E, Y in F, and all times T, saying that actually if you start one of the processes xt at point X and fix a point Y, then this is the same as actually fixing the X and starting the other process at Y and looking at in expectation. So this if this expression holds, then the two processes are called dual. And we know, I think most of us know, that duality is extremely useful, because if you have duality for sufficiently large classes of functions, you can calculate certain quantities of one process using the other one. For example, if you have a moment duality, then you can determine the one-dimensional distribution of one of the processes. So in our context, what kind of duality do we get? Of course, we get a moment duality. We just need a little bit of notation, because of course we have now vectors. So our state spaces, points of our state space are vectors. So Z is a vector ZV, V in V. With natural numbers, and X is a vector of numbers between 0 and 1. And we define H of X and Z as just the product over my set V, X at side V to the power Z at side V. So we look at this moment and this product of monomials. And what we prove for our coordinated processes is that they satisfy a moment duality in the classical sense. So we consider our structured branching coalescing process with coordination defined a few slides ago. Then there exists a Markov process X of T with state space 0, 1 to the V, such that actually this moment duality formula holds. The proof is not difficult. It's just a bit messy, because you have to write down the generators and do a lot of calculations. So you do this standard explicit generator calculation in order to obtain a generator duality. To obtain the process duality, you can apply sort of standard arguments, because we are in this simple setup where one process is discrete and the other takes values in 0, 1. The dual process can be constructed rather explicitly using Poisson point processes. I will show you on the slide after next what the dual process looks like. On this slide, I first show you what the dual process without coordination looks like, or if you want, if you put all the measures of our particle systems for the rates equal to delta zero. So without coordination, the dual process is given by this SDE, which is something many of you know. It is what is called the stepping stone model with mutation and selection, or in Invariance, they call it the resampling selection process. So you see the four terms we have with migration, branching, death, and coalescence. So migration leads to also migration in the dual process. Branching leads to this selection term, so it can be interpreted as, so the whole process XT can be understood as the dynamics of the relative frequency of a population of two types. So actually you look at the dynamics of the less fit of the two genetics types on a system of islands. So we have an island model. So you migrate from island U to island V at a certain rate. This is the selection term, or the selection parameter on island U, where actually you look at the parameter as the selective advantage of the fitter type, because here you got the, wait a second, yes, this is the selection term. You have a mutation coming as the dual transition from death here, where you mutate towards the less fit type. And here you have the usual random genetic drift, Wright-Fisher type transition. So you have a Wright-Fisher diffusion where BT is Brownian motion. So this is a population model, the stepping stone model, more or less. And now if we incorporate coordination, our dual process looks a lot more complicated. What is blue here is the part without coordination, or actually the part that comes from the atom at zero. So the atom at zero leads to the uncoordinated or the independent part of this process. And the coordinated part of this process is given here, where again, you have parts for migration, branching, death, and coalescence, or rather migration, selection, if you like, mutation and resampling, where here the ends are Poisson point processes with the intensities given by these measures, well, for each of the possible transitions times dt. So you're actually at each arrival of one of these Poisson point processes, you have at the time t, you have an y that belongs to this time t, so to speak, which determines the size of the transition. So you get a large migration also here, you can say. So you get actually a system of SDE with jumps. So you have a continuous time here that is known from the uncoordinated case, and a jump part for each of the four possible transitions that can be described via these Poisson point processes. So the dual process, take-home message, you don't need to remember, of course, the form of the dual process, is a system of SDE with jumps, which is also one of the reasons we prefer to work on a finite lattice, because we are a little uncomfortable with dealing with countable systems of SDEs with jumps. But we look at the particle systems, but it's good to know that we also have a nice dual process. So this duality is one of the structural properties of these coordinated systems. Another nice general property of this coordinated system is what we call invariance of expectation, which is something that holds for coordinated particle systems in the sense I talked about, in the case without coalescence. So on this slide, I assume that we have no coalescence, so all our lambda measures are zero. And then it turns out that if you look at the process of expectations of our of ZT, so if we look at the expectation of ZT, t from zero, running from time from zero to infinity, then actually this process, this expectation, only depends on the total mass of our measures for migration, branching, and death, and not on the particular shape of the measure. So in fact, the expectation over time satisfies this ODE, where the coefficients are given by the total masses of our measures for death, branching, and migration, and therefore can be solved relatively easily. So in particular, the expectation of the process is independent of whether or not we have coordination or not. And this is something we saw in the very first example I presented to you with the independent branching and the fully coordinated branching. So I claimed, I didn't show, but I claimed that actually the expectation is the same in both cases, and this is true in this generality. This is nice. It has nice applications, and this is why I included the parabolic Anderson model on my slides of examples, because this nice observation allowed us to a simple proof for the well-known Feynman-Katz formula for the parabolic Anderson model. So the parabolic Anderson model, this is a side remark for those of you who are familiar with the parabolic Anderson model. The others, please just ignore what I'm saying. The parabolic Anderson model is a Cauchy problem, which describes the motion of particles in a random field, if you like. And it can be understood, the solution of this Cauchy problem can be written as a branching random walk, where branching happens in a random environment given by a random potential. And the Feynman-Katz formula is a nice representation for the solution of this parabolic Anderson model. And actually, we understood that we can prove this Feynman-Katz formula in a very easy way if instead of the branching process that one usually studies for the Feynman-Katz, for the parabolic Anderson model, which involves independent branching, instead we look at fully coordinated branching processes of the same type, and then we can find this Feynman-Katz formula quite easily. And because it only talks about expectations, it's the same whether or not we have coordination or not. So proving this invariance of expectation lemma is based on the binomial nature of the events we have in the process. So the construction we had is really that every particle decides independently to participate or not, which leads to sort of a binomial number of particles actually participating in a certain event. And we can also, another result that we can prove is that so the expectation is the same for fixed total mass of the measures. And actually we can prove a related result on the variance of the process. So we can show that the variance of our coordinated particle systems over time can be bounded from below by the variant of the independent process, so with all delta zeros, multiplied by the total mass of the measures we had, and from above by the fully coordinated variant. So that's an interesting observation, that actually the independent process with all delta zeros leads to the smallest variance, and the fully coordinated process leads to the highest variance. Which is maybe natural if you consider that with the fully coordinated, you can have sort of a huge number of particles doing something, so you get higher variance. So if we have non-zero coalescence measures, these are in general not true. You can try to say a few things, but they're not true in general, these results. Okay, so this was on invariance of expectation. And for the remainder of my talk, I want to talk a little bit about the question of coming down from infinity for certain examples of such coordinated processes. And this is actually, so to start with, another nice and classical application of duality. If, say, we are interested in fixation probabilities of the dual process. So let us first assume that we are non-spatial, so my V just has one point, and we consider the dual process xt. Then we can look at the expectation of little x to the power zt, where zt is my particle system started at n, and I can send n to infinity, so start with infinitely many particles. By duality, this is the same as if I fix the n and just let the dual process started from x run. And of course, in the nature of this expression here, if we send n to infinity, x of t is a number between 0 and 1. So this expression is non-zero if and only if xt is equal to 1. So this expectation is exactly the probability that xt is equal to 1 for n to infinity. So this is the fixation probability of my dual process, which fixates if it hits 1. But the left-hand side is non-zero if and only if my process ZT actually comes down from infinity. So if the ZT at time t is finite, even if the starting point is sent to infinity. So coming down from infinity means that the process started with infinitely many particles actually satisfies that the probability that it is finite after an arbitrary amount of time t is equal to 1. This notion was introduced by Pittman for lambda coalescence and studied extensively by Schweinsberg. For our processes, where we don't just look at coalescence, we want to slightly extend the notion of coming down, or maybe just rewrite the notion of coming down from infinity. So we say that a process comes down from infinity instantaneously, and now this is not restricted to coalescence, but to any particle process, if we started at infinity and it's finite with probability 1 after any time t. We say that it comes down from infinity, not instantaneously, but after a finite time, if it's finite with positive probability. So usually it means that it's infinite for a certain time and becomes finite after a finite time. Or it stays infinite, if it stays infinite, if it doesn't come down from infinity. So if it will be infinite for all times. So these are the three options we consider. And for lambda coalescence, this is of course very well known. So in the case of lambda coalescence, so no death, no branching, and also no migration, because we first look just at lambda coalescence, non-spatial lambda coalescence. Of course, you can also look at spatial ones, but let's look at non-spatial ones. It is very well known that Kingman coalescence, so that's the case without coordination, comes down from infinity. And more generally, this is true if the coalescence measure has an atom at 0. That was proved by Pittman. So an example of a coalescent that comes down from infinity but not instantaneously is the star-shaped coalescent. That is the fully coordinated coalescent, where of course if you stay with infinitely many particles, you stay infinite for an exponential amount of time, and then at some point everybody collapses into 1. This is actually true more generally if the coalescence measure has an atom at 1. So if after some time actually everybody coalesces into just 1 particle, then of course you come down from infinity after that time. This condition is a condition by Pittman. So if the coalescence measure lambda satisfies this condition, then the lambda measure does not come down from infinity. So this condition is sufficient for not coming down from infinity, but it's not necessary. For example, the Bolthausen-Snitman coalescent doesn't satisfy this condition, but doesn't come down from infinity either. And necessary and sufficient conditions were given by Schweinsberg in his paper of 2000. So this is are some of the well-known results from coalescence. And now we want to study coming down from infinity for other types of coordinated processes. And I see that I should hurry up a bit, or I will not get to what I want. Anyway, I will stop early maybe. So one interesting coordinated process, especially with respect of coming down from infinity, is the Seedbank coalescent. So the Seedbank coalescent is the following. Here we have 2 sites, so finite number of sites, but not 1, but 2. And if we have 2 sites, of course, we have several possibilities of starting at infinity. We can start with infinitely many individuals at site 1, or we can start with infinitely many particles at site 2, or at both of them. So what's the Seedbank coalescent? The Seedbank coalescent does not have branching or death. It has on site 1 coalescence in an independent way, so Kingman type coalescence, and on site 2 we don't have any coalescence, but we have coordinated migration between 1 and 2, and coordinated migration from 2 to 1. The measures don't need to be the same. So we have coordinated migration measures, independent coalescence at 1, and no coalescence, no branching, no death otherwise. So this comes actually, so the 1 can be considered as the active population that reproduces, the 2 can be considered as a dormant population that does not reproduce, and individuals can switch between active and dormant states. That's why that's where the model comes from. And for this model, we can prove, and I showed in the talk I gave a couple of weeks ago, I gave some hints on the proof, that actually in this relatively simple coordinated process, all the possibilities of coming or not coming down from infinity may occur depending on the migration measures and on the sort of way you start at infinity. So we are in the setup of the previous slide of the Seedbank coalescent, and we consider a random variable y with distribution given by the migration from 1 to 2 normalized to be a probability measure. This is a condition that is motivated by a paper by Bob Griffith. And then we have the following situations. If my migration measure from 2 to 1 has no atom at 1, and we start with infinitely many particles in state 2, then the process does not come down from infinity. It's probably not so surprising. So if we start with infinitely many particles at the second side, and you have no atom at 1, so you have no way of moving everybody at the same time to the side 1, you stay infinite because here, of course, you have no coalescence inside 2. If the migration measure from 1 to 2 has an atom at 0, or if this y random variable has expectation of minus log y equal to infinity, and if you start with infinitely many particles at the first side, then the process does not come down from infinity either. This basically means, I mean, in the first side, you have the Kingman coalescent, which does come down for infinity. So in order to come down so in this situation, actually, sufficiently many particles move from side 1 to side 2, where they cannot coalesce in a reasonably short time. Next condition, if my migration from 1 to 2 has no atom at 0, and if this expectation is finite, and we start with infinitely many particles at side 1 and finitely many at side 2, then actually the process comes down from infinity instantaneously, because at side 1 the Kingman kicks in and you don't move sufficiently many to get rid of them. And last situation is we have no atom at 0 for migration from 1 to 2. You have an atom at 1 from migration from 2 to 1, and this expectation here is finite, and you actually start with infinitely many at side 2, then the process comes down from infinity, but not instantaneously, because at some time you actually move everybody from 2 to 1, and then the coming down from infinity kicks in. So message from this slide is that actually coordination may change this behavior of coming down from infinity in interesting manners. And in this situation, it's due to the fact that we actually have coordinated migration that changes this behavior so much. So, and I see that I should come to an end, because we also want to have a few questions. So I will be a little short on the last question. So this is another coming down from infinity question. Of course, coming down from infinity is something we associate with coalescent processes, because coalescence makes particles disappear. But the question is, of course, if we have also death, can also death instead of coalescence lead to coming down from infinity? So especially if we have coordinated death now. In coordinated death, many particles may disappear at the same time. So we could think that, yes, it could lead to coming down from infinity. So we assume lambda equal to 0, no coalescence. What would be the conditions on coordinated death and possibly on the branching measures to have actually coordinated, to have coming down from infinity just by coordinated death? And the intuition, which can actually be made rigorous, is the following. So death measures, as our branching and migration measures, have singularity of order up to 1. So we can compare a coordinated death measure to, that's the main idea, a coordinated coalescence measure, where the coalescence measure, you remember, have singularities of order 2 up to 2. So we compare the death measure with another, with the coalescence measure of this particular form. And because the death measure is finite, this measure needs to be finite. So according to Pittman, there is no coming down from infinity in this case. So this makes us believe that actually death, even fully coordinated death, cannot lead to coming down from infinity. Except, of course, if you have really fully coordinated death, then everybody will disappear at some time, but every other death measure will not lead to coming down from infinity. And this is actually true. So this is a proposition. That the process with lambda equal to 0 comes down from infinity if and only if the death measure has an atom at 1, and in that case, it comes down from infinity after a finite time. And in order to prove that, that's actually, again, a nice application of duality. If we first consider just the situation with independent death, then you already know that this doesn't come down from infinity, but you can look at the particle system, which is then a process that just jumps from n to n minus 1 at rate n. And so the dual process, according to our duality formula, is then deterministic. So it's given by the solution of the simple ODE, and therefore you can calculate the expectation of x0 to the power zt in an explicit way by plugging in the solution of this process, and you see. So this is the probability generating function of zt, and the right-hand side here is the probability generating function of the binomial random variable. So the zt is binomial and therefore does not come down from infinity. And now if we look at the situation where the death measure does not have an atom at 0, the general situation is just obtained by mixing the two situations. We do actually really define a measure lambda tilde, a coalescence measure in this way by saying lambda tilde dy divided by y squared should be the same as the death measure dy divided by y. And then we can couple the lambda tilde process and the d process by starting them with the same initial conditions. And at the coalescence of k blocks in the lambda tilde process, all of them die in the d process. And now we just have to kill single individuals, which cannot happen due to coalescence. So we do that with the appropriate rate. And then Pitman's condition actually shows us that this process does not come down for infinity, and these single killings cannot lead to coming down for infinity either, in the same manner as sort of independent death cannot lead to coming down from infinity. So let me switch that and just jump to the conclusion. So what I tried to tell you in this talk is that coordination can be incorporated in a natural way into branching coalescing particle systems. Duality and invariance of expectations are relatively easy to prove tools that provide already nice properties of these processes and some conceptual insight. And already in simple cases, coordination leads to new effect. For example, the coming down from infinity in the case of coordinated migration or coordinated death versus coordinated coalescence and so on. And of course, there are many more possibilities to include coordination into processes. And you will see that in the next talk by Andras, he will present a more, you will see what he will present. So he will present a nice coordinated process that has some interesting features. So thank you very much for attending my talk. And it's time you can ask a few questions. Thank you.